Welcome to Unit 16. We look again at critical points, and especially when critical points change. And that's related with catastrophe. It's a fancy theory, catastrophe theory. I want to say something afterwards. But let's look at the definitions. First of all, we look at functions. As usual, we look at functions of one variable. So this is f of x. And a local minimum we call now a stable equilibrium. Actually, we want to have it a strict minimum. So like here, so this is a minimum, this is a stable equilibrium. So the reason why we look at minima, not maxima, is because of physics. Physics likes to minimize energy, and so when you take a ball in a bowl here, and that's stable, right? If you take it like that on a maximum, that's unstable. That falls down. So it is important whether we have minima or maxima. And nature also tries to maximize entropy, and energy minus entropy, that's the Helmholtz free energy, that's what nature also tries to minimize. Very important principles, these minimization principles. But here we have, we are looking now at the new story. We look at the case when the number of local minima change, and that's what we call a catastrophe. That was one, the notion of stable equilibrium. Two is a catastrophe if depends on a parameter then C is a catastrophe. So parameter value is called a catastrophe if at C0 the number of stable equilibria changes. So in this lecture we will just look at examples. We will look at example which is under 3. That's the next thing we are going to do. In class we will practice in groups another story. In the homework you will practice then another story. But it's always the same thing. What we are doing is we look at a kind of a movie of a function changing. So let me just, actually before we start with example 3 there, let me just take the example when we take f of x is equal to cx squared. So that's quite a boring example, but it still will lead to a catastrophe. So what we have is we just draw for different c values, we draw the graphs. So this is c. We usually go with c up. It could also go down, but usually we go up here. And so this would be c is equal to -1. This would be c is equal to 0. This is c is equal to 1. And in each case we draw the graph of the function. So in this case, when c is -1, we have a parabola down like that. And here it's flat, and then you have a parabola. So you see that what happens is for positive c we have a stable equilibrium. And for c this is unstable. So what we have is a change here from unstable to stable. And so we say c is equal to 0 is a catastrophe. So that's the story. We will also then draw the critical points. So the critical points will always then be kind of drawn like that. In that case, maybe let's make the unstable blue, and then afterwards they become stable. Let's make it pink. So what happens is here there is a change, but it's always the same critical point. This critical point is always at x equal to 0. At x equal to 0, the derivative is 2cx, and the second derivative is 2c. So you see, when c is negative, this is a maximum, so it's not stable. Here it's minimum. So what we will have to do is to draw a lot of different cases. So let's just take a few examples. I make here kind of c going up like this. And I will also use the computer to draw this because that's can be a little bit tedious to do by hand. So let's just see that c is equal to 0. Actually, c is equal to 0 is kind of an interesting case here. And then let's just say c is equal to 0, c is equal to 1, and c is equal to 2. Let's just experiment a little bit. So c equal to 0 is the case when we have the function x to the 4 minus x squared. This is a function we have already seen. So what I do here, I draw every time just a graph of the function. So in this case, this is a function which has roots at -1, 1, 0. So it is this w function. So this is c is equal to 0. Now at c is equal to 1, I have to kind of, it's better we take a computer. I have here my camera, my laptop camera. And I have a Mathematica notebook. Kind of do that. I have it already prepared, and so I can actually kind of look at that. So when c is equal to 0, I have this situation here, and we have already seen that. So for 0.5, I have something like this. So that's actually quite an interesting thing. What happens is this is moving up, and for 0.5, what I have is a graph which looks a little bit like this. Where's my yellow? It looks like that. So this has actually kind of gone like that, and gone like that, and go. So there is still a stable one here. So if I take 1, the function still goes through 0, but it does something like that. So there is only one minimum. But why is this a catastrophe? It's a catastrophe. As we showed the movie, the equilibrium point has changed in a discontinuous way. It was here and then has here. So it actually has changed the bifurcation diagram. So the bifurcation diagram, what we have is we take c here, like before, so this is kind of the c-axis, and that's the x-axis here, equal to 0 here. And if we look at that at c is equal to 0, what we have is at x equal to -1 and x equal to 1, we have a stable equilibrium here. I also want to draw, I think I did it in pink or in purple, so I want also to draw the unstable one. This is stable. So what happens when you go up, this one is actually moving a little bit to the left, and kind of what happens is they actually come closer and closer together. So when you are doing this, there's something like that. If you look at that on the maybe here we look at it on the computer, what actually happens is that the point is moving to the left, moving to the left. Very slowly at first, but then faster and faster and faster and kind of moves like that, while the 0 always stays unstable. So this is always unstable here. What happens on the right hand side, we have also to look at that. The right hand side, it actually moves to the right, so a little bit to the right. So what actually happens is this moves to the right more here. So this moves to the right. Stable equilibrium. Very interesting. And what happens is it has disappeared around at 0.5. So 0.5 is, or something near 0.5 is a catastrophe. Cool. But if you understand this example, then you can also do the homework and understand what catastrophes are. Cool. So let's just wrap it up.